Welcome back to the SWL Tools demo video series. This video takes you through the process of quickly estimating a building's heat gain on both an hourly basis and a daily basis. I'm Mark Decay, author of SWL Tools, and I'll be giving you the tour. As you know if you saw the previous videos, the SWL Tools spreadsheets support the use of the methods and tools in Sun, Wind, and Light 3rd edition. So open your SWL Tools and click on the P2 Quick Heat Gain tab at the bottom. Even though this is the quick heat gain method, it is still a little more complex than the quick heat loss approach that we just completed. Nevertheless, it's designed to get you a fairly accurate preliminary picture of heat gain rates so that you can design passive cooling strategies for your building. That's one of the prerequisites for doing any passive cooling system design, is that first we have to establish how much heat the building is gaining and therefore how much needs to be cooled. There are two main parts to the quick heat gain: an hourly rate of calculation and a daily rate. The hourly heat gain is used to size passive cooling systems such as cross ventilation, stack ventilation rooms, and evaporative cooling towers, which are all thermally open strategies and work without mass. The daily heat gain rate is used for night-cooled mass, where the heat has to be stored in the mass throughout the day and cooled by ventilation at night. First, let's take a look at the hourly heat gain. The floor area carries over from the previous worksheets. The heat gain method is broken down into parts A, B, C, and D. This is the same structure as found in the analysis technique A27, total heat gains, that starts on page E350. So let's look at that now. So here's the first page of technique A27, total heat gains, and also it does total heat losses, which we looked at in the previous example. I'll go to the next page, page E351. Part A covers the internal heat gains of people and equipment. Remember that people are like little furnaces, always making heat, and that most all of the energy that goes into powering equipment or appliances ends up as heat in the space. Consult the table on page E351 titled Heat Gain Totals, Part A, Internal Heat Sources, People and Equipment. Find the row for your occupancy type. For residences, the table shows a range of 1 to 2 BTUs per hour per square foot for people and 1 to 2 BTUs per hour per square foot for equipment. These units, BTUs per hour per square foot of floor area, will be used for all of the rates of heat gain. As with all the tools in Sun, Wind, and Light, be sure to read the text to understand the assumptions that are built into these quick methods. The range for occupants represents average to maximum occupant density, while the equipment range represents very efficient to average efficiency equipment. I'll pick a middle range for each because I don't want the passive cooling system to fail later if the owner does not always choose the most efficient equipment, or if a bunch of extra guests happen to show up for dinner. So I'll use a value for each one of 1.5. Now be careful here. In some occupancies, equipment loads are rising rapidly. In others, the actual occupant density may not be what is assumed. You can also use the occupancy heat gain analysis technique A16 to find the heat gain rate if you already know about how many people will occupy the building or zone that you're analyzing. Let's enter the rates for occupant gains and equipment gains. So I'll close my SWL electronic, go back to my SWL tools. We're still on the P2 quick heat gain sheet. I'll go to occupant gains and input 2.5, and also we determined 2.5 was our rate for equipment gains. Next we'll look at electric lighting heat gains. In part B we look at electric lighting, which is based on the type of lighting system installed, the levels of illuminance, and the hours of occupancy. If daylighting is used along with smart lighting controls, then this can save significantly on electricity. and so therefore also on the amount of heat gain coming from the electric lights. So first you have to make an assumption about how much daylighting the building will be designed for. And to do this, we'll consult analysis technique A11, design daylight factor. So back to my sun, wind, and light electronic. We'll go over to page 310. This is technique A11, design daylight factor. We'll use the instant method in the table titled Recommended Daylight Factors by Room Use and Site Latitude. I use this table to quickly set daylight factors for both clear and overcast climates. Again, read the text to see if the assumptions match your building reasonably well. If not, you can use one of the more detailed methods to find your design daylight factor. You may remember that the daylight factor is the ratio of illuminance inside the building to illuminance outside the building. This daylight factor target will also be useful for sizing daylight apertures because larger windows are required to create higher interior daylight factors. Come down to the row for residences where we find three types of rooms. Let's take living spaces as the typical condition in the home. The IES, or Illumination Engineering Society, recommends 10 to 20 foot candles of illuminance. To achieve this with daylight, we look under one of the latitude columns. Because outside illuminance is less at high latitudes than at lower latitudes, the daylight factor recommendations also differ by latitude. Knoxville is at 36 degrees north, so I will interpolate between the recommendations for 30 degrees and 40 degrees. For living spaces, the recommendation is 1 to 1.5% daylight factor at 30 degrees and 1 to 2.5% at 40 degrees. Strictly following the recommendations, I would choose a 1 to 2% daylight factor target. But remember, these are only guidelines generated by engineers. If you want more daylight and brighter experience to the spaces, choose a higher daylight factor. If you want it to feel dimmer, choose a lower daylight factor. I like brighter spaces, so I could choose the upper end of our 1 to 2% recommendation, or I could raise it further. In fact, I'll use a 2.5% daylight factor. Later I'll need to consult the daylight aperture strategy to make sure my windows are sized to meet this goal. Returning to the total heat gains analysis technique, let's estimate heat gain from lights. On page E353, we can find the table Part B, Internal Heat Gain Sources from Electric Lighting. This is the second page of that table, and this is where we'll find the residential row. So I'll enter the table on the left with the band for residential buildings. Again, I'll interpolate between 30 degrees and 40 degrees latitude for Knoxville's 36 degrees. And then move across to the column for 2 to 3% daylight factor. Remember, I chose 2.5%, so my heat gain is in a range between 0.3 and 1.8. There's not much difference by latitude in this case. The range here is based on lighting system efficiency and goes from very efficient to average efficiency, with the average efficiency, of course, having more heat gain than the more efficient lighting. LED lighting, if used throughout, would heat even less. I'll use about 1.0, about halfway between, assuming some efficient lighting systems, but not the most efficient. And while we're here, let's record the gains for electric lighting with no daylight, which is actually the rate that we'll use for nighttime lighting. So let's look at daylight factor less than 1.5% in this column, and we find the rate is 0.7 to 4.1 for very efficient down to average lighting. So I'll split the difference again and call it 2.5. Let's enter these values on the spreadsheet. So now we're back on the P2 Quick Heat Gain worksheet, and I'll come in and put in my 2.5% daylight factor, and then we determined that the rate of heat gain using electric lights and daylighting at the same time would be about 1. Now we're ready to look at part C, heat gain through the envelope. For our heat gain calculations, we'll use the total areas for each element, including the south or solar heated side. Now, I've already input the window area for all the orientations in this little building combined. This method simplifies by leaving out skylights, which have much more heat gain in the summer than do vertical windows. If you want to approximate heat gain from skylights, just triple their area in the calculations. For windows, this method assumes that they will be fully shaded with a shading coefficient of about 0.25. That means that no sun strikes the glass and only about 25% of the heat gain makes it through to the inside, mostly by reflection. Now, this is a big assumption in many buildings because most buildings that depend on machines for cooling are not designed to be fully shaded. So here we'll input the percentage of glass that's fully shaded during the cooling season, and I've already set this at 100%, which is the default on the spreadsheet here. Often you won't know this exactly in the beginning of the design process, so what you input here becomes a critical design criteria for shading design later on. You can experiment with the shading percentage to see that poorly shaded windows have a lot more heat gain. So for instance, if I put in 50% shaded, you can see that my heat gain goes up. I'll put this back to 100%, and that's where I'd like to leave it. Now we need to add the outdoor design temperature factor from the table on page E354. Here's page E354. We're still in technique A27, total heat gains. Look at the section 1 for gains through externally shaded windows and select a temperature factor. To pick the right one, in this case, remember that our summer design temperature that we set on the Energy Targets worksheet was 90 degrees Fahrenheit for Knoxville. Depending on how you're using SWL tools, you might choose a different value. I'm assuming that I'm designing for natural ventilation, so even though it occasionally gets hotter than 90 degrees, we would not be using natural ventilation because the incoming air would be too hot. On the other hand, if I was designing for night-cooled mass or evaporative cooling, I might choose a higher outdoor temperature to cover more extreme conditions. You can interpolate between the values for 90 degrees and 100 degrees, or extrapolate below 90 or above 100 degrees for hotter conditions. For windows, our Knoxville factor is then 16. The process is repeated for walls and roofs. For walls, the factor to use in Knoxville is 15, and for roofs, 35. Notice that on a square foot basis, roofs will have more than twice the heat gain of walls. The greater exposure to the summer sun is one reason that standards for roof insulation are greater than for walls. Remember to use only the areas that gain heat to the interior, excluding roof overhangs, parapets, unconditioned spaces, decks, patios, garages, and so forth. Now let's return to the heat gain worksheet. We're now looking again at the P2 Quick Heat Gain worksheet. So I'll come down to Part C, Heat Gain through the envelope, and we need to input our outdoor design temperature factors. So we just found that the outdoor temperature factor for windows in Knoxville would be 16. For walls, 15, and we recorded 35 for the roof gains. We need to input the wall areas also, including the south side. Now I've already input for this little building the areas for window gains and the areas for wall gains. Note that the roof area is carried over from the quick heat loss worksheet. The U factors for walls and roofs are also carried over from the heat loss sheet where they were calculated as the reciprocal of the R value. Note that gains through floors which do not receive sun are ignored. The spreadsheet does the same calculations as shown in the hand formulas in Part C of the method in the total heat gains analysis technique, where we've been getting all of our inputs from. Part D calculates gains from ventilation and infiltration. The heat gain rates from infiltration and the ventilation gain are transferred from the P2 Quick Heat Loss worksheet. Input the heat recovery efficiency of the heat exchanger if used in summer. In this case, I'll assume that it's not being used, and I'll leave the heat recovery efficiency at 0. Also input the outdoor design temperature factor for ventilation and infiltration from the total heat gains part D that we looked at before. I've already input the factor of 16 for Knoxville. The spreadsheet then sums the heat gains for each element in two different totals, one for thermally open strategies that don't include infiltration and ventilation, and one for thermally closed strategies that does. There's no right answer here. Smaller is better, and larger heat gains generally mean that the passive cooling systems are going to be larger, or that there are longer periods when the passive cooling doesn't do all of the cooling work. And of course, when it's not doing all of the cooling work, that means that the active system is in play, and so larger heat gains mean larger active cooling systems. Residences in general should be under 20, and 12 is pretty low, although lower rates are possible. So down here you'll see that the rates for our building in the example here are 13.5 when the heat gain is for closed strategies. That includes parts A, B, C, and D, D being heat gain from ventilation and infiltration. And then it's 12.4 BTUs per hour per square foot for heat gain for open strategies that ignore part D, ventilation and infiltration. Of course, buildings with larger internal gains will also have a higher total heat gain rate. These results can be used to size several of the passive cooling strategies in Sun, Wind, and Light. So that's it for the quick heat gain estimate of hourly heat gains. In the next video, we'll continue with looking at quick heat gain method for daily heat gains that are used in night-cooled mass.